Welcome everyone. I'm Nikhil. I'm a postdoctoral scholar in the Department of Land, Air and Water Resources at the University of California, Davis. I handle the hydroclimatology part of our project Urban Stream Corridors. Imagine a scenario where heavy rain saturates the soil, reducing its stability. Now add strong winds to the mix. So now this soaked soil weakens the grip of tree roots, making it easier for even moderate winds to topple the trees. So such kind of events can lead to widespread infrastructure damage, blocked roads, downed power lines, and disrupted communities. So, in this presentation, I will explore how events like these, known as compound precipitation wind extremes, pose socioeconomic risks to the San Francisco Bay Area. So, what happens when climate meets inequality? This is a key question driving our research. So, globally, climate change is increasing the frequency and intensity of extreme weather events, making this a pressing issue for urban regions worldwide. So, San Francisco Bay Area is no exception. As one of the most critical urban regions globally, it is home to over 7 million people and it contributes to $750 billion annually to California's economy. But it's also a hotspot for extreme weather, particularly during the wet season when heavy precipitation and strong winds often coincide, often driven by striking atmospheric rivers. So, on top of these climatic challenges, there are significant socioeconomic disparities in the region, including income inequality and housing issues. So, together, these factors create a complex web of vulnerabilities, underscoring the need for urgent action. So, this study examines how precipitation wind extreme events trends overlap with social vulnerabilities to identify the most at risk communities. San Francisco Bay Area is unique in many ways, making it a critical region for studying compound precipitation wind extremes. First, the Bay Area is composed of 9 counties with diverse geography, ranging from the coastal areas and to the valleys and to the hill regions. So it includes major urban centers as shown in these red dots in this figure, such as San Jose, Oakland, San Francisco, and Richmond. So this diversity in the landscape plays a significant role in how the region experiences and responds to extreme weather. Now, looking at the climate here is Mediterranean with wet winters and dry summers. However, the annual precipitation pattern are highly uneven, as you can see in the figure. For example, northern Sonoma County it receives over 1100 mm of rainfall annually, while counties like Solano, Contra Costa, and Alameda and Santa Clara they receive less than 500 mm of precipitation. The wet season, which is typically from October to April, is often driven by atmospheric rivers, and these narrow bands of concentrated moisture bring intense rainfall and strong winds, leading to increased risk of flooding and wind damage across the region. So the Bay Area's diverse geography and uneven rainfall distribution create unique challenges for managing compound precipitation wind extremes. So before diving deeper into the methods and the results, let's focus on the key research question driving this study. First, we aim to understand the spatial distribution and the temporal trends of compound precipitation wind extremes in the Bay Area. This region is characterized by strong physiographic and land use gradients, making it unique. Second, we explore how these compound precipitation wind extremes they vary both within and between counties, particularly in relation to their social vulnerabilities. And finally, we ask whether this complex region faces a relatively uniform risk from compound precipitation wind extremes, or if there are distinct hotspots where compound precipitation wind extremes and social vulnerability risk overlaps, requiring targeted interventions. So these questions frame the rest of the study, and we will address each in the subsequent sections of this presentation. So, this slide provides an overview of the methodology used in the study to assess compound precipitation wind extremes and socioeconomic risks. So, the analysis is divided into two main parts. First, we identify the compound precipitation wind extremes using the GridMet dataset, which provides daily precipitation and daily wind speed at a 4 kilometer resolution. We apply the 98th percentile threshold to define these extreme events, and this is followed by an analysis of the return period analysis and decadal trends and the climate characteristics of compound precipitation wind extremes, including precipitation, wind speed, and temperature. Second, we incorporate socioeconomic data from American Community Survey dataset, which provides 5-year estimates at the census tract level. So this data is on economic status, household characteristics, racial and ethnic diversity, and housing conditions. So these variables are combined to create a social vulnerability index. And finally, what we do is we integrate these two components, the social vulnerability index and the compound precipitation wind extremes, and using spatial analysis to identify the risk hotspots, areas where high compound precipitation wind extreme frequency overlaps with high social vulnerability. So let's delve into the methods and the results of a crucial piece of our methodology, that is the 98th percentile and the return period analysis ahead. So, what exactly is a compound precipitation wind extreme event? So, if you can see the figure, on the x-axis of the figure, there are wind speed variable and the precipitation variable. On the y-axis, we have time. So, day 1, day 2, day 3, and all the way up to day 365. So these red dotted lines, these are the 98th percentile threshold for wind speed and for precipitation. And these stars, these are the different values of the precipitation and wind speed on these days. So, according to our definition, which is a compound event occurs when both precipitation and wind exceed the 98th percentile at individual grid points. So, in this case, day 1, where the 98th percentile for both precipitation and wind speed is exceeded, is registered as a compound event. So, this methodology is called a peak over threshold method, which is used to separate these daily bivariate events. So, now that we have identified what a CPWE is, you might be curious about how often these events can occur. How do we calculate their frequency? Like in our study, we firstly determine this through the return period. So, how the return period has calculated? So, if you can just see the figure, it is the same figure from the previous slide. So, in this case, we have one event. Let's say if we have one event, one compound event in the whole 365 days. So, so we calculate the return period. It is the inverse of the probability of an event. That is, if we have to calculate the return period in years, that is number of years in the study period divided by total number of events. So total number of events in this case is 1, and the number of years in the study period is also 1. So that means that the return period is 1 year. That is, such event is happening like every year for this particular data. So there is a very important point, like which is noteworthy, that we have taken into consideration the wet season from October till April. So, this is because post summer, by September, the soil typically exhibit significant dryness due to prolonged dry periods. Therefore, the starting month is selected as October. And like in the wet conditions in the April, that is, sustained moisture is present like after a rainy season, and so any precipitation event can initiate flash flooding. So therefore, the ending month is October. So this map illustrates the 98th percentiles of precipitation, and this represents the 98th percentile of the wind speed. So the first map represents the like 98th percentile at an annual scale, the second one at on the wet season, and the third one on the dry season. Similarly for the wind speeds as well. And this is the legend for both of the 98th percentile for precipitation and wind speeds. So in terms of precipitation, we can see that the 98th percentile are relatively higher in the wet season than annually, like as it is expected, because the 98th percentiles in the wet season would be higher because it's the wet season. And but in terms of wind, the wind percentile values are slightly higher in the wet season compared to the dry season, but the difference is very subtle. This slide highlights the return periods and the intensity of compound precipitation wind extremes in the San Francisco Bay Area. So, first, the Bay Area is clearly a hotspot for compound precipitation wind extremes, with events occurring almost annually. For most of the regions, as you can see in this figure, the return period range from zero point 0.5 to 2 years, indicating very frequent occurrences. However, like coastal Marine County, it stands out for having a slightly lower frequency compared to the other regions. So, second, when we look at the compound precipitation wind extreme intensity in terms of precipitation, we see that the coastal and the elevated regions, they will experience the most severe impacts. This is largely due to exposure to the Pacific storm systems, and which are further or like amplified by orographic effects such as wind lifting over these coastal ranges. Now that we have identified the frequency and intensity of compound precipitation wind extremes, we move on to trend analysis. We created a 10-year moving aggregate of compound precipitation extreme events, frequency, along with a 10-year moving average of precipitation and wind speed and temperature. So, this would help us uncover its long term patterns and trends. So, now let's dive deeper into the methods that we used and the results that we found. So how we have like collected our data? So what we did, if you see the figure, so this is the similar figure that I showed in the previous slides, just extended up to the maximum temperature and minimum temperature. So these are the values for day 1, day 2, and all the way to day 365. So as we can see here that for these are the thresholds for precipitation, these are the threshold for the wind, and there are two compound events which are registered. So what we do is we take these compound events and we make a table sort of like this, and which registers the compound event ID, the date, precipitation, wind speed, maximum temperature, and minimum temperature. So once we have this data set for all the grid points, then we generated the 10-year moving average time series for this precipitation, wind speed, maximum temperature, and minimum temperature. And also, we generated a 10-year moving aggregate time series for the frequency. And after doing that, we conducted a mean and trend analysis using Man-Kendall test and SenseLoop. So now moving on to how we have conducted this trend analysis. So the trend analysis, it consists of mainly two steps. One first step is the Man-Kendall test, which is a non parametric test to determine if there is a statistically significant trend in the variable using statistics based on pairwise comparisons. And the second step is the sense slope estimator, which is used to quantify the trend, like to estimate the rate of change using slopes between all pairs of data points. So, median slope is called sense slope. So, what flowchart we have followed in this study is we've done the man candle test and we have followed this table, the z value of 1.96. So if the value z value of 1 is greater than 1.96, that means it is showing an increasing trend and it is statistically significant. And if there is the value is from minus 1.96 to 1.96, that means the our trend is not statistically significant. And if my value is less than minus 1.96, then it means that it has a decreasing trend and but a statistically significantly decreasing trend. So this is for the 95th percent confidence level. So in this example, if you can see, this is our time series of annual precipitation, and in the graph we can see there is a increasing trend. So if we apply these tests for this time series, we should get values which satisfy the criteria for the increasing trend. So the values that we get is we get the Z statistics of 3.04. That means it has statistically increasing trend. And we get the sense slope of 18.57 per year. That means that the rate of increase of annual precipitation is this 18.57, which is increasing. So that's why like in studies we use this trend analysis to detect trends and the quantify trends. Moving on, we have conducted this trend analysis for frequency of CPWE events. So, what this figure tells us, this is the mean frequency of CPW events of a 10-year moving aggregate, and this is the sense slope of the 10-year moving aggregate series. So, we have shown only the significant trends here, which have this like confidence interval of 95%, and it is for the wet season and during the period of 1982 to 2022. So the results of the mean analysis, mean 10-year moving aggregate, shows that there are about 14 events per decade, which is the spatial mean over the Bay Area. And the sense slope also, it has very interesting results that we found that these events have increased in the recent decades for a large segment of the Bay Area. So now we also conducted the analysis for precipitation and wind magnitude during these events. So we calculated the 10-year moving average time series and then their means and the sense slope. So the figure on the first row, this is for the precipitation, and the second row is for the wind. And the first figure is for the mean precipitation during these events, and the second one shows that how this precipitation has been increasing during the past decades. So what we got is that the results for the precipitation were quite interesting. The precipitation during these compound events, they show a significant increase of 0 to 0.5 per year, that is this green color, in major segment of Bay Area. Like on the contrary, for the wind speed, wind in these events show a significant decrease in major segment of Bay Area, but the magnitudes are very small. So moving on further, we also calculated the temperature magnitude during these events, and so this figure shows here the 10-year moving average of maximum and minimum temperature during these events for the wet season during 1982 to 2022. So the first row shows the mean maximum temperature and the mean minimum temperature, and the second row shows the sense slope. So what we found was that the temperature trends were not that significant, but the major finding was that during these events, the maximum temperature over the Bay Area was approximately 13.5 degrees Celsius, and the minimum temperature was 7.9 degrees Celsius. Now that we understand the patterns of compound precipitation wind extremes, let's explore how these events intersect with social vulnerabilities in the Bay Area. So, next, we focus on the socioeconomic analysis, which integrates social vulnerability index, spatial clustering, and the compound precipitation wind extreme exposure. So, this approach identifies the hotspots where the frequent compound precipitation wind extreme regions overlap with high social vulnerability. We'll explore the social vulnerability. The Social Vulnerability Index is a tool used to assess a community's ability to prepare for, respond to, and recover from disasters. It is calculated using the data from American Community Service 5-year estimates aggregated at the census tract level. So these factors are grouped into these four themes. The first theme, socioeconomic status, which includes variables like poverty, unemployment, and housing cost burden. The second theme focuses on household characteristics such as age distribution, disability status, single parent households. The third theme examines racial and ethnic minority status, and the final theme addresses the housing type and the transportation challenges, including multi unit housing and lack of vehicles. So each variable here is ranked using a percentile method, which compares a census tract data relative to other areas of the Bay Area. So these rankings are combined to produce a overall SVI score where the higher values indicate greater vulnerability. So this methodology helps us identify communities that may require additional support during extreme events, guiding disaster response and resource allocation. Here we show the results of social vulnerability index analysis. So on the left side, this figure is for the overall social vulnerability index, and these are its four contributing themes. And on the right side, we have a box plot which shows the values at a county-wide scale. And so this one is for the overall social vulnerability index, and the other four are its contributing themes. So, what we found here was that in the urban areas such as Oakland, Richmond, San Jose, and Hayward, they demonstrated consistently high vulnerabilities across multiple themes. And these challenges can stem from the different socioeconomic issues such as housing pressures and minority demographics. Also, we found that in the rural regions such as Napa and Sonoma, they also show elevated vulnerabilities, particularly due to factors like mobile homes, lack of transportation access, and group quarters. And it is very important to note that we found a significant inter-county variation in social vulnerability index. So what it means that even within more affluent counties like Marine, we have localized hotspot of vulnerability. So but in general, we saw a trend with the racial and minority ethnic minority, it drives the social vulnerability index. As you can see in this black circle, we have Marine County and Sonoma County where the vulnerability levels are low, and the overall social vulnerability index is also low. But as you can see in this red circle, we have the racial and ethnic minority vulnerability high, and these hotspot urban centers they also lie in this same region. So it these racial and ethnic minority it drives the social vulnerability index in the Bay Area. And this trend, the people of color with low socioeconomic status, it is a well documented trend across the United States. So this results emphasize the need for localized policy interventions which are tailored to address the specific vulnerabilities of both urban and rural communities. So, this slide highlights the intersection of compound precipitation wind extremes and social vulnerability. So, we have taken return period of compound precipitation wind extremes and the social vulnerability index here. So firstly, like as we have already discussed, the San Francisco Bay Area, it's a recognized hotspot for compound precipitation wind extremes, with return periods ranging from zero point 0.5 to 2 years. This means most areas experience these events nearly annually, and with the coastal regions like Sonoma and Marin County, they see more intense compound precipitation wind extremes in terms of their precipitation due to their geographic proximity to storm systems. So, when we examine the intersection with the social vulnerability, the clear patterns emerge. So, Marine County that stands out for its resilience with fewer compound precipitation wind extremes and also lower social vulnerability compared to neighboring areas. However, the key urban centers like Richmond, Oakland, Vallejo, and San Jose and like Santa Clara, they face both frequent compound precipitation wind extremes and high social vulnerability. So further, we carried out bivariate LISA analysis between return period of compound precipitation wind extreme and social vulnerability index. It was done to statistically confirm the spatial correlation between these two rasters. So this is our exposure raster and this is our social vulnerability raster. So so, so this method this identifies spatial clusters based on patterns of autocorrelation. So positive spatial autocorrelation occurs when high the return period of compound precipitation wind extreme values are surrounded by high social vulnerability index values, forming high clusters, and also, when low compound, this return period of compound precipitation wind extremes are surrounded by low social vulnerability index values, that is, low clusters. And conversely, there are negative spatial autocorrelation. So, a particularly critical finding here that we found was that there was a presence of low high clusters in the areas like San Jose, Vallejo, and Fairfield. These are regions with frequent compound precipitation wind extremes, but relatively low social vulnerability. Additionally, high clusters were relatively less frequent compound precipitation extremes. They coincide with the high social vulnerability areas, which were identified in these coastal urban centers such as Berkeley, Oakland, and Richmond. So, to wrap up, here are the key conclusions from this study. First, the San Francisco Bay Area is a global hotspot for compound precipitation wind extremes with the return periods from zero point 0.5 to 2 years, meaning these events occur almost annually in most areas of the Bay Area. Second, there is a clear increasing trend in compound precipitation wind extremes, likely driven by the broader impacts of climate change on extreme weather patterns globally. Third, the key urban centers, both coastal and inland, such as San Jose, Richmond, and Oakland, they have emerged as the hotspots where high compound precipitation wind extreme frequency overlaps with high social vulnerability. So, this highlights the urgent need for the targeted adaptation measures to protect at most risk populations. So, finally, the future research would focus on projecting compound precipitation wind extremes using the downscale climate model data across different scenarios, and this will help us better anticipate risks, guide adaptation strategies, and build more climate resilient communities. So ultimately, collaboration across disciplines, combining climate science, socioeconomic data, and urban planning, is essential to protect vulnerability communities in high risk regions. Thank you for watching this. And if you have any questions, we'd love to hear them. Thank you.